Hello, everybody. Thanks for joining today. We'll get started now. So, my name is Rajiv Chakrabarty. I'm an account executive here at JETRO, and I'm joined by a couple of my colleagues here. Yuval Shetty, he is a solution architect here at JETRO, and Dylan is also going to be joining us. He's going to be manning the chat rooms. Some housekeeping items before we kick off. We're going to have a Q&A session at the end. In the meantime, if you have any questions, please feel free to ask those questions in the chat room, and Dylan will actually go ahead and help answer those questions. So with that, let me get started. So some of the topics that we're going to be covering today, we'll start with some of the business intelligence on big data challenges that we face today. We'll look at some of the SQL and Hadoop architectural approaches that we commonly see in the industry today, and there are different ways to handle different use cases. We'll then dive into a demo on using Jethro with Tableau and Click on Hadoop. After that, we're going to dive into a Jethro technology overview, some more details around what is the technology behind how Jethro performs. We'll then transfer it to Yuval, who's going to give you a quick demo on how to set up Jethro. And then we'll discuss typical use cases and dive into some Q&A. So today, when we look at how typical BI tools function, you have the BI tools. They are pointed to different data sources. It could be some of the traditional data sources, like relational databases or text files or Excel files and things like that. They are extracted into memory, and there they are put in a column format, compressed, and then the BI tools are able to enable business users and end users go slice and dice the data, do ad hoc data discovery, and things like that very, very quickly, very, very interactively. But as the sizes of the data grows, two things happen. One is the extracts tend to take longer and longer, and then also the performance of the BI tools keeps dropping, and at a certain point they completely choke. So typically when that happens, the usual process is to then push down the queries through some form of a live connect into the underlying data source. And we have Hadoop here. That is the direction that people are going. But even if it's any other data source, whether it be something like an Oracle SQL Server database or any other data source, the idea is to then push down the query to the data source so that you solve the problem of scalability in terms of the number of rows you can access. However, then you're bound by the number or the performance of the data source itself. And typically, the performance does not match up to the in-memory performance of the BI tools, and consequently, it is a much slower approach. So given that scenario, we have, over the past decade or so, we have a lot of end users or customers and companies going towards the big iron appliances like the Oracle Exadatas, Teradata, and IBM Netezas of the world, and they upload a part of the data into those appliances, and then put the BI tools on top of that and use Live Connect to be able to get the performance that they need. However, obviously, those come at a cost. They're not cheap, and also they're not open platforms. So as the cost of storage has kept going down, and with the advent of Hadoop and the ability to process a lot of data, customers have been moving to a Hadoop platform, and that obviously provides cheap storage and cheap scalable storage and high resiliency. And that makes sense to be able to store large volumes of data at low granularity, all forms of data, structured, unstructured, semi-structured, and and that allows cheap storage. However, with the advent of Hadoop also, people have found that while certain workloads like ETL workloads or machine learning workloads, predictive analytics work fine with Hadoop, BI happens to be too slow. The reason for that is, as we all know, Hadoop was originally meant for batch-oriented workloads. MapReduce takes time, and while that is fine for certain badge-oriented tasks like ETL, it is not okay for business intelligence, wherein you have interactive queries coming in and end users expect fast response times. Nobody wants to sit there and see the hourglass spinning. They want to be able to do data discovery at the speed of thought. And that's what they've been used to with some of the BI tools like Tableau and Click, etc. So Hadoop obviously uh, solves the scale performance, scale problem and cost problem, but performance is too slow, especially for BI use cases. So how do people normally solve this problem? And there are multiple ways to skin the cat. And obviously, the first thing that people think of is to add more hardware. So whether you add additional nodes or you scale up by adding additional RAM, CPU, the idea is to go ahead and reduce the number or the amount of data per node so that you can process a query and do MapReduce in a reasonable time frame. Obviously, that is not a sustainable approach because over time, as the data size grows, you have to add additional nodes, and the Hadoop um, cluster that you have is already processing uh, data for many different use cases. So that is not obviously, like I said, a sustainable approach. So a common approach that people use is to have a whole bunch of um different, a look at a different number of different SQL on Hadoop engines, starting with Hive, which is probably the most prevalent out there, and a lot of people use that. Then there is the Impala, Drill, SparkSQL, Hawk, Presto, Actin, a whole bunch of them out there. Each one has their own advantages compared to the others. Impala was one of the first ones around, coming from Cloudera. Obviously, Presto came from Facebook. Presto and Drill allowed the ability to go ahead and query many different data sources and uh, query the data sources where they exist. However, all of these, including Spark, which is obviously the in-memory technology, uh, all have a common thread, and that is they're all what we call as MPP, massively parallel processing full scan technologies. And I'll get into what the inherent problem that those technologies have with respect to, in particular, BI use cases. And then you have the NoSQL and Hadoop. So people tried putting Phoenix on top of Edgebase and trying to do operational analytics on it. Obviously, then again, there are technologies like Kylan, which has now provided the ability to do traditional OLAP cubes on Hadoop. However, they have some inherent problems as well. So you have to have a semantic schema, same semantic layer, which is fairly complex to do in an OLAP cube. It also inherently means that the data will be aggregated, and so sometimes you lose the granularity of data that you need, especially when you're storing data in Hadoop. You might need to denormalize it into a large table. So and in some cases with cubes, the amount of time it takes to go ahead and update the cube is prohibitive. So people start going through these different types of technologies, and when one fails, you go to the next one, and then when they find that some of these are not working, you go back to some of the tried and tested methods of the past decade, which is you store the data in Hadoop, then you go back from Hadoop back to an EDW like Netezza or Vertigo, and try to get some performance. Obviously, some of those available as a platform as a service or a software as a service like Redshift and Snowflake are being used extensively now. Um, but then again, there are the MPP full scan technologies as well. And then some other customers have tried something different. They've gone and looked at something like Elasticsearch and put indexed everything and use search engines and then put a Kibana like flexible analytics interface on top of it. So there are many different ways to skin the cat there. However, the most commonly used one has been the SQL on Hadoop edges. That's what we find in the market. And when we look at them, there is, like I said, one common thread. They're all MPP full scan technologies. And if we can explain what they do essentially with an analogy that we like to use. And if you think about that, essentially in that architecture, you take your data and chunk it up so that each node is executing over a small data set. So if you look at the analogy, if you have a library with billions of books and you have thousands of racks, you need almost a librarian for every single rack, and then each librarian would go, and when they're looking for to create a list of books by Stephen King, they would go ahead and pull book by book by book from each of those racks, and then compile that list. Obviously, that is a very resource intensive task to do, and when you have a simple query like that, which is looking for books by a particular author, it'll take a long time to come back. So as opposed to that, if instead we had a fully indexed architecture, what would we get? What we get is in the same scenario, we would know exactly which where the Stephen King books are, which locations they are, and on which rack. And we would need a single librarian to go ahead and go to the locations and pull the books and create a list of those books. So that's what is inherently the architecture behind Jethro. Essentially, if you are able to take all of your data and index everything, then we would be able to answer those questions across vast volumes of data much faster and also consume far fewer resources, making the query scalable over larger volumes of data. However, if you think about it, what we're not suggesting that it's a one size fits all. Um, the full scan architectures actually do coexist with the indexed approaches, meaning the full scan architecture would probably be a better fit for um, for uh, for use cases like ETL, for use cases like predictive analytics or large scale reporting, where you need to access almost the entire data set to come up with a result set. So many of the queries or use cases out there where you would go ahead and require to read all of the data set would be best suited for SQL on Hadoop solutions with the full scan MPP architecture, like an Impala, Presto, or SparkSQL. However, um, for the use cases where you would go ahead and only uh, require access to BI applications and look at the regular BI patterns where people go ahead and start off with a dashboard and then they slice and dice. They go ahead and drill down and do ad hoc queries and ad hoc data discovery. The indexed approach that Jethro follows actually works much better. So if you look at the chart that is on the right-hand side of the slide here, you'll see that the full scan access tends to take much more time for something like live dashboard and interactive ad hoc queries. Um, However, as you go towards complex analytics or full ETL, the full scan access starts getting better. So again, these two different types of technologies actually can coexist, and they complement each other depending on the use case that they need to service. So that gets me to what Jethro actually is. So obviously, you know now that Jethro falls in the latter category from the previous slide, which is a fully indexed architecture. But what we essentially do is that we are an acceleration layer for BI and big data. So we sit between the BI tools, like the clicks and the tableaus of the world, and the data that they need to work on to provide the visualizations and the dashboards on. And we basically work across all of the workloads or use cases that fall under BI, and that includes regular reporting, dashboardings, ad hoc data discovery, slicing and dicing, and customer self-service BI. And how does it work? It basically is a combination of an indexing and caching server. So on the outside, it works like a columnar SQL database, very much like Vertica. And on the inside, it actually utilizes an indexing architecture like a search engine like Elasticsearch. So we are a tool which combines both of those into one product. We do have partnerships with official partnerships with Tableau and Click, but we work with many other tools um, like Business Objects, Spotify, MicroStrategy, and also custom BI applications. And on the Hadoop side, we work with all of the major Hadoop vendors. We're actually certified on them. And so in addition to Cloudera, MapR, Hortonworks, we also work with Amazon EMR, Apache Hadoop, and so we pretty much cover the entire Hadoop spectrum in terms of the different distributions available. So as I mentioned, Jethro is an indexing and caching server. We have ODBC and JDBC drivers. So any BI tool that can utilize an ODBC or JDBC driver to connect to Jethro can and utilize the Jethro server to submit SQL queries. So Jethro has a full-featured ANSI standard compliant SQL engine. That is what the BI tools connect to. So from a BI tool standpoint, it appears as a regular data source. The ODBC and JDBC drivers are available on our website, and you can download it. And they also include the ability to load balance. And I'll get into that a little later. So some of the key performance features that Jethro has that enables that Jethro to be that BI acceleration layer over billions of rows of data is full indexing. So we index every single column and every single table. And by default, it is not something that a DBA needs to sit down and decide. We, by default, index everything. So we're fully indexed architecture. Also, in addition to that, we have a query result cache. So every single query that hits Jethro, it is cached. And so if the same query comes in again, we go in and pick up the result set from the cache and return it. Also, we have a feature called auto cubes. Essentially, we look at the incoming query patterns and we generate micro cubes, and we store those cubes in Hadoop on HDFS as well. So that's another important point, is that our indexes, our column files, our auto cubes, and the query result cache, they're all stored on HDFS in Hadoop, and there's no data really stored on the Jethro nodes themselves. Those Jethro nodes are stateless. And so once you have indexed the data, typically historical data, we would be able to go ahead and incrementally update the data or add incremental data to it. And that works very fast, very quick. It's a fairly simple process to do, and you can run it every day, every hour, every minute. That would keep the indexed data within Jethro updated and at very fast rates, so that you can be near real time. So let me go ahead and jump into a quick demo where I'll show how to do how to use Tableau against Jethro. So here we have TPCDS open source data set, which is a sales related data set. The fact table itself has about 3 billion rows. It's about 400 GB raw of raw data, and there are about 7 dimensions. So we actually did a benchmark against Impala and Redshift as well. Now this is a site which is accessible from the outside. So if you go to tableau.jethrodata.com, you'll be able to access it yourself, and you can try it out yourself. The login is demo, and password is demo. Now let me jump into the into so this is the dashboard I was talking about. It's, as you can see, is in Tableau. And we start off with about 3 billion rows. So let me go ahead and select a year. I'll select 1998 in this case. And it went ahead and accessed the JETRO server and came back with a filtered set here of the entire dashboard with about 544 rows. So initially, when we started out with the dashboard, obviously there are no filters, and this dashboard itself issues about 12 to 15 queries back to JETRO. Now let me go ahead and select a category. I'll select books. And as you can see, it came back pretty quickly, and it's now filtered down to about 54 million rows from the original about 2.9 billion. Let me select a store here, bar, and you can see that it's come back with about 210,000 rows. Let me go ahead and select on the good credit rating, and it's going and running that query, and it's come back with about 51,000 rows. So one of the important things to note here is that as you keep drilling down or filtering the data more and more, the queries performance from JETRO gets faster and faster, and that's because the data set over which it is running is getting smaller and smaller. This is in sharp contrast to some of those full scan MPP technologies, in which at all points in time, no matter what the query is, they'll pretty much work on the same full data set. So let me go ahead and hit revert here so that it goes back to the top level dashboard. Again, in this case, since we had hit this dashboard once before, it was stored in the query results cache, and so it came back very, very quickly. Let me go ahead and now edit this dashboard. So let me go ahead and pull this out. So you have your dimensions, your measures here. Let me go ahead and add net profit. And this at this point is, if you go back to the dashboard here, you can see that there are no other filters here. So it's working on pretty much the entire data set. So let me go back here. And so I added a net profit. I'm going to go ahead and add adjusted profit as well. And then I'm going to go ahead and from this dimension, I'm going to pick state and add, in addition to the city and store, I'm going to add state here. As you can see, it is running against a large set of data, a lot of rows, and it comes back with very, very interactive performance. I'm going to go ahead and revert. And go back to the dashboard here. So that gives you an idea of how quickly it performs. And I'm going to go back to the presentation. So what we have done here is when we did run those benchmark results against both Impala and JETRO, and Impala in this case is representative of most of the other full scan technologies out there. And what we found is, while Impala takes about, on average, 90 seconds for the different types of queries, JETRO averages about 6 seconds. Most JETRO queries come back in a range of about 5 to 10 seconds. If you look at the blue line here, you'll see that when you hit the main page, so on the one side you have the main page, which is not heavily filtered, and the main page comes back very quickly because a lot of users actually land on that dashboard page, and so it gets quickly cached. And as you keep moving towards the right and you keep adding filters, and it gets more differentiated between what different users might be doing out there. The indexes kick in and provide fairly consistent performance across the board. So again, JETRO performance usually ranges between almost instantaneous when it's hitting the query result cache to about 0 to 10 seconds in average. And one other important thing to note here is that as you keep adding filters, JETRO gets faster and faster because of the use of the indexes. However, a tool like Impala or any other full scan technology, the time it takes to return gets slower and slower as you keep adding filters, because with each additional filter, it requires to scan an additional column. So how would you go about using JETRO? So essentially with JETRO, we're looking at a BI relevant data set. JETRO works with structured data only. So whether you have that structured data available in any data source like an EDW, like Netezza or Teradata or NoSQL database, it's available in delimited text files or in Amazon S3, or you already have data in a data lake on Hadoop. You can take that data. JETRO will run that through a JETRO loader and create an indexed set, which it will store back on HDFS on Hadoop. That index set will include index files and column files, essentially what it needs to be able to provide very good performance out of the index data itself. So once the indexed BI data set is created, it does not need the original data set anymore. All of the queries that come to JETRO will then be serviced entirely by that indexed BI data set. And then after that, periodically, as new data comes in and lands in any of the data sources or the BI data set on Hadoop, original data set, we would then keep loading them incrementally and adding to the indexes that we've already created. Now, one important thing to note here is that the indexed BI data set is stored on HDFS, but that's not the only location that can be stored. It can also be stored on a local file system. It can be stored on S3 or EFS in an Amazon. It can be stored on a network file system. Essentially, the storage of the indexes can be in multiple different locations. It's not entirely dependent on Hadoop. But Hadoop HDFS obviously makes a good location where we store, because we take advantage of the low cost storage in Hadoop, the scalability and the resilience that Hadoop provides. Also, the index loading process is fairly quick. It loads between half a billion to a billion rows an hour, and when we create the index BI dataset, the final size of that is about 1/3 the size of the original data set, the raw data set that we started with. So we get approximately 3x compression there. So let's talk about how index access works. So in this case, we're storing our index files on HDFS. So it's spread across a number of data nodes across the Hadoop cluster. And then again, if it's not an HDFS, like I said before, it could be an S3, it could be an EFS, it could be a local file system. In that case, it is stored across multiple disks that forms part of the file system that is stored on. So you have a data node, and you have an incoming query, sum of sales by date, where product equals books. And it comes and hits one of the JETRO query nodes. And it's important to understand again that the JETRO nodes are stateless. So it pretty much uses compute to be able to return the result sets. So in this case, when it receives this query, it goes ahead and hits the indexes. It identifies the row IDs where the data is stored. Those are returned to the JETRO query node, and then the JETRO query node goes ahead and hits the column files, which are again stored in HDFS to retrieve the data, and only the data required for the rows that is being accessed for this particular query, and returns it to the BI tool that issues the request. So That again, like I mentioned before, the performance of Jethro is based on the size of the working set. So if this particular query accesses about 10 million rows, irrespective of whether you have 10 billion, 50 billion, 100 billion rows, total rows in your data set, it will only access the 10 million rows and will provide consistent, fast performance. And so is which is which is which is a very different from the full scan technologies, again, which would access the entire data set to be able to return this query. One other thing that is important here is to understand that as your data size grows, to be able to get whatever performance you're getting out of a full scan architecture, you would need to go ahead and keep adding additional data nodes to be able to get the same performance. Whereas Jethro since its performance depends on the working set size, that is not the case. So let's talk about a little bit about the indexes itself for Jethro. So again, every single column and every single table is automatically indexed. The indexes are inverted bitmap indexes. There are highly compressed hierarchical bitmaps, um, a format that we came up with. So, and basically what we do is we store the values and then we store the corresponding row IDs. Now, indexes obviously have been around for a long time. They're not new. And indexes have always provided very fast access to the data, especially when you have a filtered query coming in. However, the penalty that you pay is when you update the indexes. So at that time, you have to lock the indexes, and that causes blocking and performance impact typically to the queries coming in. However, we circumvented that problem by never updating the indexes. So anytime we get incremental data, we do not update the index. We always append to the existing indexes. So as an example, you see that you have France here, which the data France, which was in row IDs 2, 9, and 10. And you get some additional data where there's France again. And we do not go ahead and update the existing row in the index. We actually go ahead and append to it. Um, and we have a structure called an index of indexes, so it knows where exactly those fragments are. So when a query comes in, we can go ahead and fetch those rows very, very quickly. And periodically, we have a background maintenance thread which wakes up and looks at the indexes and compacts the indexes which are highly fragmented. And it does this also in a non-blocking fashion, which does not impact incoming queries by first doing that index and then replacing it. So at any point in time, you can go ahead and keep updating the data at very, very quick intervals, and it will not affect the performance of the incoming queries at all. Also, we create indexes of all types. We create function indexes, join and composite indexes, depending on the structure. Jethro supports star schema, so you do not have to denormalize into a single table, and we are highly optimized with the star schema star join. So we go ahead and create the indexes that we need to make that happen. Also, we have a patent on this technology, and you see the patent here on the slide. So let's talk about the second performance feature that we mentioned, which is query result caching. So again, every query that Jethro gets is cached, and we cache intermediate results also for high reusability. Um, and we store these the query results cache again on HDFS on the file system. So that allows us to store thousands of cache queries, and also allows us to for additional Jethro nodes when they're deployed for them to be able to directly read the indexes and not and keep the Jethro nodes themselves stateless. And so incremental refreshes work very well. So just like in indexing, we go ahead and add to the existing indexes with incremental data. With the query result cache, when you have additional data coming in, that is not the cache does not get invalidated. What we do is we run the query against only the incremental portion of the data, and then add or merge the two sets together. So the query result cache is always updated with additional data. And one important thing to understand is that this is very complementary to indexing, because um, while indexing works best for certain queries which are highly filtered, um, the query result cache actually works with the other side, where we get queries like the queries coming from the dashboard, where they're not highly filtered, and so those queries get cached very quickly because they're used by many users, and we provide consistent performance across the board. So auto cubes, yeah, we what we do is basically we look at incoming query patterns like you have what you see here. So essentially, what we do is we go ahead and create very small cubes as opposed to large cubes. These are created automatically behind the scenes by Jethro, and they're maintained automatically by Jethro, including the addition of incremental data. So we can create thousands of such cubes depending on the incoming queries, and we can also create complex expressions like case distinct, if then else, as opposed to simple min max mean. So these are again complementary to indexing and the query result cache, and it again looks at a certain set of queries that would benefit from this, and those queries get hit these cubes, and they're automatically created and maintained. So in terms of concurrency features, the Jethro nodes themselves are stateless, like you mentioned. The ODBC and JDBC drivers, they have inbuilt ability to go ahead and load balance across multiple Jethro servers, and they do it in a round-robin fashion. And that allows them to go ahead and share the cubes, the query result cache, as well as the indexes across multiple Jethro nodes. So they can be brought into circulation very, very quickly. And again, Jethro nodes are so let me go ahead and jump to the structure. So the Jethro nodes actually are mostly installed as an edge node, and all they need is the access to the HDFS file system. So they work off, they need an HDFS client, and they'll connect to the HDFS file system and be able to do what they need to do. So it kind of offloads the CPU and memory requirements off of the Hadoop cluster, and that's been very advantageous to several of our customers, because then the Hadoop cluster is available to do other kinds of use cases like ETL and other applications requiring a MapReduce and SparkSQL. So it can take the BI workload off of the Hadoop cluster, and just Jethro servers will then only access the HDFS storage layer to access the index BI dataset, the Jethro cache, and the cubes to be able to service multiple BI applications. And these BI applications, again, can be BI tools. It could be custom applications executing ad hoc queries. So some of the use cases that we see out there is large-scale BI that we talked about, where the challenge is either to be able to fit the number of rows in memory in those BI tools, or the extracts are taking way too much time. And if you have the data stored on Hadoop, you're moving from an EW to Hadoop, you're doing EW offloads, that you need fast interactive BI over large volumes of data. Also, if you have an existing Hadoop cluster which is being used with Impala, and you're trying to put, or Hive, and you're trying to put a BI application on top of it, and it is bringing down your Hadoop cluster to its knees with a lot of concurrent users accessing it, you can offload that to the Jethro nodes, which are the edge nodes, and it'll be able to utilize it. So top reasons to use Jethro: consistently fast queries, because every column is indexed, results are cached, and microcubes are built automatically. Data model flexibility is an important one, because we allow you to go ahead and access data at the lowest level of granularity. You do not need to sacrifice the number of years of data that you need to store. There is no need for pre-aggregation. We do that on the fly, and we get our performance from indexes, the query result cache, and the auto cubes. And partitioning, we offer partitioning, but it's just primarily for data loading and deleting of data. We do not need partitioning for performance. Operational simplicity is an important point again, because most of the functions that we perform, including indexing, incremental update of data, is most of the structures that are within Jethro are automatically maintained and made usable. So it requires minimal DBA time and engineering time to maintain and update. Typical use cases replaces the need for external EDWs like the Netezas and Teradatas of the world, but it complements other SQL and Hadoop tools depending on the use case that you're using it for, as I mentioned earlier. So before I go here, I would like to turn it over to Yuval, and he will give you a very, very quick.
Actually, I don't think he's ready to have time. Instead, let's ask for Q&A.
Okay, maybe we don't have time for that. We'll do it next time around. Let's go for a quick Q&A section. So there's a question, how much space does indexing every column take? So I'll take that first. So essentially, like I mentioned before, when we index it, so if you have about a terabyte of data, raw data, uncompressed data that you have, and if you go ahead and index it, we compress it we get about 3x compression, so we'll get about 300 gigabytes of additional space that is required there. The result cache, there are parameters in there that you can specify how much of space that you can offer to the result cache. And is it FIFO? I will let. But is it first? So I'm just gonna. I'm just confirming that yes, the result cache is FIFO. So the second question I can see is, do indexes need to be rebuilt to reduce performance reductions caused by fragmentation? And the answer is no. We've never seen, we don't see that. The fragmentation in the indexes is taken care of by the maintenance thread that I mentioned. So essentially, it looks at the indexes and compacts it, and automatically generates a newer version of it and replaces it. And every time we go ahead and update the data, it will go ahead and add to the indexes. You do not need to recreate those indexes. So IBM Big Insights. So we obviously we have tested with Hortonworks, and IBM Big Insights, from what I understand, is an ODPI compliant distribution of Hadoop. In fact, currently we are in conversations with IBM to go ahead and certify ourselves against IBM as well. But because they are ODPI compliant, JETRO will work on the IBM Big Insights distribution as well. But we'll keep you updated on our interaction with IBM and how we're progressing against getting it certified. But it should be soon. So yes, if it is, so the other question is, if it is an ORC originally, then it is basically a duplicated data volume to index. Essentially, yes. So in JETRO, we do use a columnar data format to store our index and column files on HDFS, but it's not exactly the same as ORC. We use a proprietary format because that's one of the things that allow us to get very fast performance. And so from that standpoint, yes, if you have data already in ORC, or whether you have data in raw text files on Hadoop, we would need to read that data and create our own indexes, because that's how we get a performance. The way I look at it is it is a bit of an overhead, but given the fact that Hadoop allows cheap storage, and we compress it to about one third the size. That is a small price to pay for the performance that you get for the BI applications, which otherwise would not be able to run at the speeds that you need it to run. So currently we are not on. So we can install on any of the public uh, public clouds. So whether it be AWS or Azure or others, we can work with them. We're not on a public cloud marketplace per se as of yet, but that is something that we have talked about, and that is something that we might be doing fairly soon. So one of the questions there was is how do you handle snowflaked um, schemas? So we do. So like I said, we do not require you to have a denormalized table. If you do have a denormalized table, it works fine. But we work across star and snowflake schemas as well. So we have the ability to do joins like any other SQL engine. Our SQL engine is fully ANSI 92 compliant, so we'll be able to handle any kind of joins coming in, and we work very well with most of the queries that are issued by most of the popular BI tools and custom applications that we see. So can you handle streaming data from such as from Spark streaming? Yes, we can. However, you would currently have to land it somewhere. So as long as you're able to land the data somewhere for temporarily, so that we can go ahead and use JETRO loader to go ahead and index that data, we would be able to utilize the data coming in from Spark streaming to make it available to the BI tools. So, so hopefully that answers some of your questions, and this was a useful presentation for you. And if you have any further questions, please let me know. And you can go ahead and download JETRO from jethro.io, and it is free to evaluate. So go ahead and download it and start using it. If you have any questions, you can submit it to support@jethro.io, or you can send it to me or Dylan, and we'll get back to you. So with that, we've come to the end of this webinar, and hope you have a great day and a great week. Thank you.